In lecture 5, we are going to study how to deal with electromagnetic wave in solids, especially in terms of momentum and energy. And we are not going into the detail about the mathematical procedures, but we mostly cover the necessary fundamentals to understand the further study of the band structure and following the energy diagram to think about the photoelectrochemical processes. So the first one is the energy level. And of course, in any photochemical processes, we need to understand the electronic states in molecules and the solids. And in this case, solids. So what's the difference between the molecules and solids? And the key difference is in the case of solids, there are so many atoms involved, meaning that there's some periodical structure of the atoms, which makes some kind of special treatment. And first of all, let's review the Schrodinger equation. Oh, before going to that, again, the electromagnetic wave itself is classically we can deal with by the Maxwell equations, and that's totally same. And when we think about the materials, so we need to think about the energy of electrons, and to understand the energy of electrons, we use the Schrodinger equation. But in the molecule case, we basically apply the Schrodinger equations for the wave function, meaning that the wave of electrons, and you could obtain the structure or shape of the electron cloud and also energy. But in the case of solid, since the material has some sort of the larger periodical structure, we have to think about not only the energy, but also momentum of the wave, or wave, not only the electromagnetic wave, but also the electron wave we have to think about. Okay. So at first, let's think about in a classical theory that, as you know, that momentum is given by the h over 2 pi times k. If it's three-dimensional, it's a vector. So which is equal to h over k. So k is wave vector, right? And similarly, energy of light is given by h nu. So which is sometimes equal h bar omega. So omega is angular frequency. However, in quantum mechanical theory, we cannot directly obtain the value of momentum and energy until you apply the mathematical procedure to the wave function. That's why in quantum mechanical theory, you have the momentum and energy as operators. Operators means some mathematical procedure, but until you apply that mathematical procedure, you cannot obtain the value. Okay. So in the case of the P, which is a momentum case, in a classical theory H bar K, but in the quantum mechanical theory IH bar, and then the ddx, ddy, ddz. So if you have some functional form, and this mathematical procedure is operated, as you can see, this is vector, and you can obtain the vector of momentum. And in the case of energy, as you know, which is mostly called Hamiltonian, and Hamiltonian is equal to 2h bar squared over 2m and number and u. This is a potential energy, so depending on the material. So again, this one is also a mathematical procedure to the function. So until you apply this calculation, you cannot obtain the values. And as you know that in the Schrodinger equation, so this is called a wave function. So this, once you know the wave function, and you can obtain the energy value like this. So this is energy. Like that. So, and what makes the problem a little bit complicated in the case of solid is we have to again we have to think about not only the energy, but also we have to think about the momentum. So just briefly, and so in the case of molecules, if we have a two energy level of the ground state and excited state, and this energy gap matched was the light, it can the energy can be absorbed. But in the case of solid, not only this energy matching, but also if you eliminate the light, the momentum of light, and there's some electron cloud, and this electron is also kind of wave. So electron has some sort of the wave number and momentum. So the momentum of the electron and momentum of light must be matched too. So this is the difference between the molecular case and a solid case. So this things is that's why we have to think about dispersion relation, which means the conversion of conservation of energy and momentum. So dispersion relation indicates the relation between the energy and momentum. So at first, let's think about the light case in one-dimensional case. So as you see that, so in the case of light, epsilon equal h nu equal h bar ck, which is you can just easily convert that nu is C over lambda, right? And then so you can convert and then K equal 2 pi over lambda. So you just convert it to K was and obtain the epsilon equal H bar CK. So this is, you can see that this is a relation between the energy and the wave vector, right? So if you draw this one, obviously epsilon and K for light is a linear line with a slope of H bar C. But when I think about the electrons, especially for simplest case, we now think about the free electrons, meaning that the potential energy is equal to 0. And then I don't go into detail, but this is one type of the wave function of free electrons. So psi equal exponential ik r, and just put that wave function in this equation, and this one also kind of given in the, this one is given in the exercise after lecture. So please try to calculate it, but not a big deal. So, and then you can obtain the epsilon k equal 2m p squared equal 2m h bar squared k squared. So this relation indicates the energy is now the proportional to the square of k. Right? So if we draw and k for free electrons, it's like a parabolic curve. So as you see, for the light absorption of the interaction between the light and the free electrons, you need to have a much of not only the energy, but also not only energy, but also the momentum too. So to have an interaction between light and electrons, so yeah, you need to have a matching of the energy and the momentum.